Notacon.
Okay, so my name's Melinda Minch. I'm getting my master's degree at Case. I'm in the software engineering lab. My specialty is software testing and reliability, and I need to not walk in front of the projector. So what we do in my lab is software testing research, we do software security research, we do some kind of IDS stuff, and I'm mostly on the software testing side. So this talk, the idea for this talk came because I've been going around job interviews, I've been doing some internships, and I've been seeing and getting an idea of what different companies are using for their test infrastructures. And I've been seeing that though these infrastructures are not very similar across the board, some places have very formal structures for testing, some places have almost no structure at all, it's very ad hoc, but a lot of them have common goals for improving what they're doing. And one of the common goals that I've seen in my latest experience has been automation, or more extensive automation. Places want to automate their tests further, or they want to automate them at all. So this made me wonder, what's next? What's the big buzzword that we're going to see in maybe 3 or 5 years for software testing? And so I'm here to make some conjectures about that. So before I get started, I should warn you, I'm not a psychic. I'm the most familiar with my own research, so I may not be representing the entire body of cool software testing research that's going on. Also, I do have limited industry experience because I've been stuck in my ivory tower for God knows how long. So these are the grains of salt that you should take from this talk. Alright. So before I get started with the meat of the talk, I should say, if you have any questions or comments or anything, just raise your hand, etc. I don't want to be like talking for the whole hour or however long I've got to talk. If you want to jump in with anything, go right ahead. So I'm going to talk about 4 main topics for this talk. I'm going to talk about profiling. I'm going to talk about operational testing. There's going to be some test selection and prioritization, and a few little domain-specific techniques. So here we go. So when you test software, one thing that you want to look at is what's going on inside the software. You see it running, and it's sort of a bit of a black box, right? And you can look at the code and see, you know, what this code is supposed to be doing, but you don't know exactly what's going on. And profiling is a way to sort of look inside the black box and see what's going on while the software is running. And there are a lot of profiling tools available for testing right now. There's sort of performance profiling and tools that profile memory usage, like Rational Quantify, like Bounds Checker, which checks for buffer overflows and stuff like that. So while your program under test is running, they take a look at it, they see how much memory is getting used by what functions and where. There's also some test code coverage profilers, like Clover. So they take a look at your software while it's being tested, and they say, okay, so all of your tests covered X percentage of your code. What current research wants to do is step this up a little bit. And one way to do that is to look at the flow of information in your program. So when I've got a data flow profile, I want to see what happens between the time a variable or some other piece of data is defined or initialized and when it's used. So let's take a look at my little example here. I've got a user somewhere putting confidential data, maybe it's medical records or something, into a web interface that my company's written. And I want this web interface to end up at some kind of data processor. You know, this data's going to go through there, and it's going to get processed by something that's, of course, secure and all that great stuff. I've made sure it's HIPAA compliant. But in between there, I've used somebody else's input validator, just because I want to make sure that nobody's trying any SQL injection attacks or stuff like that. So I'm just taking one and plugging one in. I got it from somewhere on the internet. You know, maybe my friend Bob wrote it. I don't know where it came from. So this confidential data is going to flow through this input validator. Now, I might have all the security in the world here and here, but right here might be vulnerable to exploits. I might have some fields that should be private and aren't. I might have some functions that call stuff in here that maybe display something somewhere or can be called by software that's exploiting this thing. So I have an information leak. And information flow profiling is one way to expose those. Another thing that information flow profiling is good for is taking a look at object-oriented design. So if you have two classes, so I've got class A and class B. Let's say I've got B looking at a bunch of A's information. And I want to say, okay, maybe B depends a little bit too much on A, or maybe I want to separate this out into another class C. And looking at information flow is one way to take a look at your code and maybe change things around a little bit or refactor. Also, data flow can help you trace the impact of a bug. So if I've got a bug in here, then I know that when this bug rears its ugly head, stuff in here and in here is going to be affected. And maybe not in classes where information doesn't flow from the web interface. There are a couple kinds of data flows that you can look at. So the first kind is explicit. I've got a variable y, and data is flowing from x to y, because I have an assignment from x to y. The value of y depends directly on the value of x. There's also implicit data flow. So the value of y depends indirectly on the value of x here. So if x is greater than 3, y is one value. Otherwise, it's a totally different one. So you might not think of the implicit flows as being an information flow, and a lot of people overlook these, but they're there, and they can be used to gather information. Is this making sense to everybody so far? Yeah? Alright, cool. Now on to something completely different. So when you're running a program, your program's probably made up of functions, God help you if it isn't, and you want to know whether they're being called, how many times they're being called, and this is good for debugging. You know, you want to know when this piece of code is being called, when it's being used, and why. So function call profiling can count how many times each function is called during a program execution. And it can also, if you want to save space or time, you can maybe say this function was called or it was not called. So you can either count them or you can just say yes or no. So this can answer some questions. It can answer which functions show up in failed executions. So if you have your program crashing 30 times out of 100, and there's a certain function that always shows up in that crash, and it doesn't show up anywhere else, that's a pretty big hint. You should look there. You can figure out which functions are used the most, so that you can optimize them, so that you can make sure that they're really tight, they don't have any bugs in them, concentrate a lot of effort on them. And you can figure out which functions appear together, which can affect your design. So maybe you know that one function always calls another function, so you might just lump them together into one big one for some reason. From function calls, you can go to basic blocks, which is about the same as a function call, except it's more finer grained. So here I have a picture of some code, and a basic block is a piece of code that if the first statement in it is called, you know the last one's called. So let's look at my blue one. For this basic block, I know that if this statement is called, then do different stuff is also called, because it's in one block, it's in one path of control. So the green one is a block, the blue one's also a block. So if you have a bunch of these, you can look at your code and break it up a little bit more than function call profiling. Maybe you have a lot of really big functions, so this would be more feasible for you to do and it would be more useful. It also takes more resources though. Something that's a horse of a different color is operational profiling. And this doesn't really count anything about the software itself as you are using it. It counts stuff about the software in the field. So it's collecting data about the environment in which the software is running and about the way that the software is being used. So this is used when you put your software in beta testing or you send it out to a customer or something like that. And you can count things like a range of inputs. So if I've got function 1 and I've got function 2, maybe if I want to profile over a range of inputs, I can say, okay, at this customer site, function 1, 90% of the time, its arguments are integers between 1 and 10. And function 2, 90% of the time, its arguments are integers between 4,000 and 6,000. You can optimize your code and debug accordingly. There are certain things that you have to watch out for depending on your range of inputs and what people are actually doing with this stuff. You can also collect information about the data types that are coming into play in your program. So if you wrote your own B tree or something for this software, and it's kind of crappy and it has a couple memory leaks, maybe it doesn't matter so much if on all the customer sites, only 2 of them are ever being used at one time. Maybe you can concentrate your debugging efforts elsewhere. But if you have 50 of these crappy B trees going around in memory all at once at all of your customer sites, then you need to tighten your code up a little bit because you're going to have some problems. Finally, operational profiling can collect information about the deployment environment. So let's say that you designed your software to be run under Windows XP with a certain amount of RAM and all that great stuff, and you find out that 90% of your customers are running it under Windows 98 with like a hamster on a wheel, then maybe you should change the way your code's working. So the reason this is research and not used in industry right now is because there are kinks to work out with it. Profiling takes a lot of overhead. You have to write a profiler, first of all, that collects data about all this stuff. Sometimes you have to go through and instrument your code, which means that you insert statements of code inside your functions to count how many times they get called or something like that. And it also generates a ton of data. So if you've got one software execution that takes 10 minutes, you've got 3,000 functions being called, or 3,000 function calls in it, and you've got maybe 10,000 functions to look at, you're going to have a lot of stuff to sift through, and you're going to have a lot of information to work with. And if you can't handle large amounts of information, or if you don't have a process set up to do stuff with that, then you might be in trouble, and it might not be very useful. Any questions so far? Yeah. It's... Yeah, absolutely. It's possible to write a high-level wrapper to do something like that. They do. You can use the bytecode engineering library in Java is a good way to do it. You can take a look at the compiled code, the compiled class files, and inject stuff in there. One ideal use of aspect-oriented programming is for profiling. So you can define your cut points at maybe the start of a function call, insert code that way, and you're done. But there's still a factor of overhead with the profiler, especially at runtime. So you have the profiler running also, you've got this extra code running also, and that takes time too. But yeah, good question. So that was profiling. And profiling gets used in a lot of places, and it gets used in everything in the rest of my talk. So now we're going on to operational testing. Current operational testing techniques are alpha and beta testing, where companies will eat their own dog food, so to speak, or send it out to a subset of users. Another variety of operational testing that you all have probably seen is the little box that comes up when your Microsoft program crashes. It says, would you like to send information back to Microsoft? And that's a form of operational testing. It sends a mini core dump back to Microsoft, and they extract information from it. And another type of operational testing is feedback buttons. In some beta software or some shareware that you see, there's a little button in the corner that says, click this to give us feedback about our software, and you can send them a message. So taking this one step further is observation-based testing, and this is the stuff that my lab does, or one of the things that my lab does. So the crux of observation-based testing is that more information should be gathered in the field using things like profiling. And you can also use things like, employ techniques like statistical testing once you get profiles, and you can also do things such as capture replay. So you've got a bunch of user profiles, right? You sent your software out to users, you instrumented it for profiling, you've got mounds and mounds of data back from them. So what do you do with all this stuff? Well, one thing that you can do is you can cluster your executions. So this is a picture of JTidy executions. JTidy is a pretty printer for HTML written in Java. And what my lab did, my good friend Pat did, was take the executions and cluster them according to similarity. So these are function call profiles clustered according to similarity. All these ones in this blue cluster here had similar numbers of functions, well, had functions called similar numbers of times. So, you know, function A was called 30 times, function B was called another number of times. These are all very similar. And you can see that they're very distinct. So this is useful in order to visualize what people are doing with your software, what's going on in there. So let's say that this pink cluster here is full of failures. I know that because all of these executions are similar, they're probably failing because of the same bug. And even, you can take this a step further. If you get a new execution profile from the field, you can put it into the cluster, you can put it into this picture and say, alright, where does this go? Maybe it goes into the pink cluster, and you can say, oh, this is probably a failed execution caused by the same bug as those. We already know about this bug, so this isn't a great big deal. This isn't anything new, you know, we're working on that, we're fixing it. Maybe you get a failed execution that's, you know, off in this corner over here. Maybe it's a new bug, so you should look at it more closely. So one way to use clusters is to figure out which failures are related. So you have a bunch of execution profiles. Some of them are of executions that failed, you know, maybe it crashed, maybe something was the wrong color, maybe somebody missed an HTML tag, maybe JTidy printed it out wrong. Failures can be different for bugs. So one bug can cause a bunch of different kinds of failures, right? Maybe the same bug caused the crash as caused the missing HTML tag. So when you cluster your failures, you can figure out that, yeah, these look different on the face of it, but they're actually caused by the same bug. You can figure out which new failures are caused by bugs we already know about, like I said. You can figure out which bugs are causing the most failures, statistically, over your group of beta testers using your software. So you have maybe 10, I don't know, maybe 100 beta testers using your software, you've got 1,000 failures. You know that 3 bugs are causing 80% of those failures. That's a good start. You can concentrate your effort on those 3 bugs. And you can figure out what profile data those failures have in common. So if one function is consistently showing up in all of these failed executions, you can say, oh boy, we'd better look at that one. So another thing that you can do with all of this data that you collect with profiles is statistical testing. So in statistics speak, you can calculate an operational distribution of your profile data. So let's say I have, I don't know, my monster truck simulator, and I've got a function, start engine. And I can say, in all of these executions, start engine is called 1 time by 10% of them, you know, 3 times by 70% of them, and so on. So you know that the majority of executions call this function a certain number of times. And you can do that with all your functions, and in that way you can make your offline tests random over the space of that distribution. That means, what are people actually doing with your software? If one function gets called in 30% of executions, then for statistical testing, 30% of your tests are going to call that function. And this is a good idea because people are going to use your software in ways that you don't expect. That's just a given. Users are the biggest source of entropy in software development. Once you ship it out to them, you don't know what they're going to use it for, and you don't know why. And the way that people use your software is going to change over time. So the research that I do is mostly stuff with compilers, because it's easy to automate input, output, you know, you've got a bunch of C files, you've got a bunch of .out files, you're done. The way that people write C code changes over time. So the functions in GCC that get called in 1997, the distribution of those is going to be different than the distribution of the functions that are getting called in GCC now. And that's just an example of how this is working. So we go from statistical testing to calculating an operation. We've got, you know, a distribution of profiles to see exactly what the users are doing. But this is a way to get a better picture of what exactly the users are doing, because you're capturing exactly what the users are doing. So when you see capture replay in a testing context, usually that means you have a GUI test automation tool. And that means that you've got some software tester somewhere sitting down in front of WinRunner and clicking here, clicking there, typing something in, pressing enter, and saying capture. And they're putting that into a test suite, and so that they don't have to sit down and do that 50 times for their software. That same series of clicks and typing and all of that is automated, and it's going to get run later. What we want to do now is do that backwards. So instead of having a tester say, make the software do this, we're going to collect executions from the field, we're going to capture them in that way, and replay them back at the company, back offline. So when you have capture replay, you're taking exactly what the user has done with your software. You're saying they clicked here, they clicked there, they entered this information, and you're replaying it later so you can see exactly what they did and when they did it. So this is like a tech support professional's dream, right? How did you mess this up? What did you do? I don't know. Now you can know. It's useful from a beta testing standpoint because you can see where the user is floundering. Maybe your interface isn't very intuitive in some way. So they're clicking around, they're trying to do something, they don't know exactly what they're doing. So maybe you can see that a lot of people are doing that and change something around for them that way. And you can also see what exactly the steps were that they took to elicit this bug that happened when they used the software. Like profiling, there are some kinks to work out in operational testing. First and foremost for me is the confidentiality issues. Whenever you send information back to a company, you're sending information about what you're doing with the software and the information that you're using the software for. And so companies may or may not be ethical in what they do with this, and they may or may not be ethical in terms of the information that they collect. I see this as a big problem, and I don't know, it's a big question in software engineering research as to how to solve this and how to make sure that everybody's on the up and up with this kind of thing. Yeah. It seems better to be used in a beta test just because capture replay has a lot of overhead. You have to collect all of these different GUI moves and things like that. So in release software, it would be an awfully big performance hit for all of your users. But if techniques for doing this improve, or if maybe the software isn't, it doesn't matter how slow it is, there are some things that it's okay if it's not exactly real time and people don't want the results immediately, people might leave capture replay in for that. Yeah. Yeah. Yeah, absolutely. I mean, if people get this thing for free as a beta test, then you can ask them to sign their soul away and use all of their information for it. If you're releasing it, yeah. Yeah, if you're releasing it, then there are a whole nother set of issues. Do you have a question back there, or you're just chilling? Okay, cool. So there's the same issues with profiling as well. There's a lot of overhead, like I said. You have to instrument the code for capture replay, or write some sort of capture replay device that you can inject code with later. And it also generates a lot of data that you have to do stuff with. So, yeah. Yeah, it depends on exactly what kind of detail you want. Yeah. So if you want to do everything down to GUI moves and down to, like, the most difficult part of capture replay is getting the threading right. So if you have a multi-threaded program, you have to collect all kinds of information about which threads terminate and do what and when, so that your replay is exactly the same as what you captured. And so that's a lot of information, and that's pretty hard to do, and that can slow things down a lot. But yeah, it does depend on what kind of application it is. So if it's like, one example that I'm thinking of is that somebody used it in a Genie application, which is like distributed Java code. That, you don't want a lot of overhead for that, because you're talking over the internet between computers. Any slowdown is a pain. But if it is something like Microsoft Word, you've got human factors, you know, people are typing, people can only type so fast, then that wouldn't be as bad. Yeah. So now we're getting, finally, to the meat of the talk, which is test selection and prioritization. And this is one of the hottest research topics today. How do you figure out which tests to run and why? It's a big industry issue, and most of the software testing research in test selection and prioritization focuses on regression testing, because regression tests are what gets run day in, day out. Sometimes people are on a continuous regression test cycle. And so if you can prioritize which tests you use, then you can have your regression testing be more effective. So what is this? What is this thing? So you've got your problems, you've got your big test suite, you've got your thousands of tests. You know that some of these are more effective than others. And you know that you have only so many software testers, you've only got so many computers, you've only got so much time, you've got 3 weeks instead of 6, you've got, excuse me, $10,000 instead of 50. How do you make sure that your software gets out on time, tested well? How do you find as many bugs as you can in this limited resource space? So obviously, this seems like an obvious point. You run only the tests that'll be the most effective that time. Oh, great. What does effective mean? So an effective test suite is going to find as many bugs as possible at the lowest cost possible and do it consistently. And that means if you run it 1 week, it's going to find a bunch of bugs. You run it the next week, it's going to find just as many. It's not going to fall off over time. So the way to select your tests is a way to make sure that your test suite is fresh, to make sure that it's finding as many bugs as it can all the time, and to make sure that you get the most bang for your buck from your test suite, basically. So at this point I should mention that test selection and prioritization, you can think of them as sort of the same problem. They're two sides of the same coin. So if you have 15,000 tests, and you sort them in order of which one is going to be most effective, that's prioritization, right? You can say test 1, 2, 3, 4, 5, just run them all, but run the most effective tests first. Whereas selection, you just take the top 25% of those and just run those. And because of the law of diminishing returns, you know, the more tests you run doesn't necessarily mean that you're going to find more bugs. Selection is pretty much as good as prioritization in this way. Does that make sense to everybody? Okay. So the questions you want to ask for these things are, what's likely to expose faults? Which tests are the most likely to find bugs? Or, which parts of the code have the most bugs? Which tests test those pieces of code? Or, which behaviors cause the software to fail the most often? If you're asking that question, then you'll run the tests that go through those behaviors. Which tests exercise the most frequently used features? If you want your program to look great for 99% of your users, You know that 99% of your users use the software in this way. They use X, Y, and Z functions consistently, and they use X, Y, and Z features. Then you're going to hit those features really hard, and maybe leave the 1% of the people who use this, mail merge or whatever in the dust. So, which tests? Do you know anyone who uses mail merge? I don't know anyone who uses mail merge. All right. So another question to ask is, which tests achieve large amounts of code coverage as quickly as possible? One thing I should mention is that it is not possible, or it is not feasible, to reach 100% code coverage. Again, it's the law of diminishing returns. If you've got 100 tests, you run 50 of those, maybe they'll cover 90% of your code. You can run another 50 and cover 98% of your code. There have been a lot of research studies done that show that 100% code coverage is not feasible. It takes a very long time to reach 100% coverage. Just want to throw that out there. So some solutions for this are to run only tests that exercise the changed code and code that depends on code that changed. So if you've got regression tests and you fixed a bug or you added a feature, you know which pieces of code changed and which pieces of code didn't. And you can use control flow or data flow profiles from your tests running to know which tests are going to exercise these pieces of changed code, which code depends on that code that changed, and which tests to run first or only to figure out if you've got any new bugs in your software. You can use dependence graphs to do this. So maybe you've got your handy UML graph of your software, you know that this function has a little arrow to that function, you've got a little cloud over here that says this data is going there. But as you develop software, your software can change. Duh. Your UML diagram may not change with your software. It may not keep up. You may have unexpected information flows or data flows from one class to another that your UML diagram doesn't cover. And so that's why dependence graphs or UML diagrams are less precise for this purpose. They're pretty good. If you don't have time to, construct a data flow profile, UML is better than nothing. But profiling is ideal for this. Another way to select or prioritize your tests is to concentrate on code that has a history of being buggy. So if you know from your function call profiles that you've collected from the field or from tests or from wherever that functions X, Y, and Z always have bugs in them, and they keep getting them, and they're fragile and they break a lot, then you're going to run tests that exercise those. So this third point probably looks a little mysterious. Run only one test per bug. How do you know which tests are finding which bugs? You don't have a crystal ball. You don't know which test is going to find a bug. How do you know which tests are going to elicit bug number 342 when bug 342 hasn't been found yet? Well, the answer is that this is a regression test suite, and you have regression bugs. And you know that these may come back. You fix a bug, 3 weeks later, you've got it back. And so when you know which tests elicit which bugs, historically, you can know which ones are going to cover which bugs in the future. So let's pretend I've got my clusters here. Let's say I've got a cluster of these 5 tests here, and I've got these here. So these are execution profiles of tests on the software, and I've clustered them. Let's say that this is one bug, and this is bug 2. If I want to prioritize my regression test suite, I can say, I'll just run one of these, and run one of these, instead of running all of them. Maybe on the next test cycle, I'll pick a different one from each cluster, just for the sake of variety, or for the sake of not running the same tests over again, or finding new things. Some more ways to do this are to run the tests that cover the most code first. I talked about that before. So Also, you can run the tests that haven't been run in a while first. Again, we're talking about regression testing. So if you've got a regression test suite that's being run every week, maybe you ran, a subset of these tests this week. You've got a bunch of them that weren't run since August. You're going to run those now. Maybe you'll find some bugs that have been in the software since September. Another way to do this is to run the tests that exercise the most frequently called functions first. If I know from my execution profiles that I've got my monster truck start engine function and it's called 9,000 times per execution, you're going to get a lot of benefits from running tests that exercise this thing first. Because when you find a bug in this function that's being used over and over and over again early, you can fix it early at a lower cost, and the bugs aren't going to propagate through the system. So you're not going to have a bunch of software failures from this one bug. Profiling and operational testing can collect data, and you can use that data to figure out which tests that these are going to be, which tests are going to be the most important for you to run this week. And there are a lot of automated techniques to do that. You don't have to sit down with your profile data and, go through it with a pencil and say, well, okay, let's look at that test. You can write a tool that takes profile data from your program, or from your program while it's being tested. It sifts through that and says, these are the tests that are going to be the most effective according to these criteria, and it spits those out, and I'll say, alright, let's run those. Any questions so far? Everybody with me? Alright. We're almost done. Another issue in test selection and prioritization is granularity. So, what I mean by granularity is, if my test suite is fine-grained, it's made up of smaller tests that test things that are a little bit more specific. Excuse me, I'm going to open my bottle of water for a second. For those of you who don't know, I'm sick today. Trying to fall over. Alright, so fine-grained tests are easier to prioritize because you have more of them. So you have more little tests to look at, you have a larger subset of things to sift through and take a look at and order. Does that make sense to everybody? Okay. So fine-grained tests may pinpoint failures better. So you've got this test that's testing one little thing, it's very specific, it's like 3 lines of code. You know exactly where that's going to fail when it fails, because you're testing something extremely specific, and all of these tiny fine-grained tests are orthogonal, they all test something completely different. But fine-grained test suites can cost more and take more time, because, as I said, they can be harder to write. If you've got one big test that is, is kind of like throw stuff at the wall and see if it sticks, as opposed to something that is crafted to poke at your software in a very specific way, it's going to be more difficult to write something that is more specific like that, and it may not generalize as well, and it may cost more time to run all of these tests. Okay, for the last topic in my talk, I'm going to go to domain-specific techniques, and these are some things that I've seen at software testing conferences. I've seen a lot of papers that have to do with topics in software testing research, but applied to this stuff. So maybe I'll see a bunch of papers on profiling, then I'll see a bunch of papers on profiling with components. So one of the big buzzwords is components. You've got things like Genie, you've got things like NetBeans, you've got things like .NET that you can take components and use them over and over again. And so I would watch for that. I know that components are already a big buzzword in industry, but they're huge in software testing research right now, so I figured I should mention them. There are also domain-specific languages. So if I have something like, let's use the healthcare industry as an example again. If I have some healthcare software that I want to write and I have a programmer who kind of knows what they're doing, maybe what I'll do is I'll craft a domain-specific language for a piece of software that I have to have them do things, to make a plugin or an extension to this piece of software. So let's say that I have an accounting program for some healthcare software, for some people in the healthcare industry. And, sorry, let me start over. I've got an accounting program. I know that some people in the healthcare industry are going to use it. So I'm going to craft a domain-specific language that has functions like bill patient, it has functions like tabulate, it has functions like send to insurance company, things like that. So that people who aren't master programmers can write this stuff. This software will generate code for them and do what they want. And so that's a pretty big thing in software testing right now.